Well, good morning, everybody. I'm really happy to be in North Carolina. I appreciate Buck saying I know the marketplace here, but I have a feeling it might have changed since 1971 when I was here. My math doesn't work that quickly in my head, but I'm pretty sure it's more than 40 years ago, and I'm pretty sure Raleigh and Greensboro look a lot different today than they did when I was there. Anybody remember Henry Kissinger? Okay, he was Secretary of State, pretty well-known guy, right? So I heard a story that you know, so many people would introduce him as a man who needs no introduction, Henry Kissinger. He says, you know, maybe I don't need an introduction, but I want one. So Buck, thank you very much for that nice introduction. I really appreciate that. Okay, let's see what we got here. I did go to NC State University, graduated with a mechanical engineering degree. I can use that curriculum vitae because I'm an adjunct lecturer at the University of Arizona. How I got there is kind of funny. Our ASHRAE group put together a team to teach us fundamentals in HVAC because the professor had retired and we couldn't do it. So I still have it framed. I have a letter where they offered me a non-paying, and then they really stuck it to me, non-tenured position as adjunct professor. So until they fire me, I'm not quitting. So I am an adjunct professor, and I can use all that fancy words there when I put my life story up here. As you can see, I've had a lot of jobs. As a matter of fact, I'm not even sure I've ever had a real job. The Trane's been great to me, and I really enjoy what I'm doing now. Kind of winding down a little bit my career and heading toward retirement. I also went to Belmont Abbey, which is right down the road. I had a great experience there. And the rest is probably pretty boring. Did anybody go to NC State? I had a chance to kind of walk through the campus there, and my first semester I lived in Syme Dorm, and I'm told, I didn't see it, but I think it's still there, and walked down that road. But my recollection, as you get to Harrelson, there's a lot of bricks. I'm pretty sure they're still all there. And when I would walk to class, you know, I would, there's always somebody working on the bricks, and I don't know whether they had the pipes or they were, you know, cutting up roots or whatever they did, but they're, you know, it was good that they had that flexibility of moving bricks. So one week we're walking, and you know, they're working on the bricks, but they weren't doing anything else. They're just taking them up and putting them back down again. So, so I had to ask, right? So I asked the guy, I said, you know, I've been coming by here for 3 or 4 days, and, you know, and he looks at me and says, "Are you an engineering student?" I said, "Yeah." He says, "You're an engineering student, and you don't know that we've got to flip those bricks?" I'm like, okay. So I figured that rather than send these guys home, you know, they'd send them out to flip bricks. They had to flip every brick at NC State. They needed a crew of about 100,000 working night and day for the rest of their lives, okay? So, what's that? There you go. Yeah, all those transferees from Carolina. So, so anyway, let's have some fun today, but I'll try not to flip too many bricks during the course of our discussion here, and you know, kind of talk about some stuff that you can take back with you and earn that one CEU or whatever you're getting for coming to this. Here's what I thought we'd talk about. I'm going to take a little minute. You may have heard that this is a 100th anniversary of the founding or incorporation of Trane Company, and you know, there's only a few people in this country that can remember farther back than I, and one of them sitting over here. But 100 years is pretty amazing to me. And it's also the 75th anniversary of our CenTraVac. So I thought we'd do a little history of the CenTraVac, and let's talk about what we're doing today. We've got a couple of exciting new things we're getting ready to announce, our new oilless chiller, and also where we're going, what's our next step, and everybody's asking about refrigerants, so I've prepared a few slides, and we can talk about that. So as Buck said, if you have any questions, I'll do my best to answer them. I'll be around for a good chunk of the day. So if something comes up later, that's okay too. Or if you have any questions, just raise your hand. I'm yours for at least an hour. So let's take a look at the Trane CenTraVac. Trane actually existed before air conditioning did, and James Trane was a plumber in La Crosse, Wisconsin, started manufacturing valves and steam specialties. We really got on the map when Reuben Trane, James' son invented fin tube radiation. That may not seem like a big deal, but it was the replacement of the cast iron radiator. I live in an old house in Newport, and I've got cast iron radiators, and I'm glad I have them. But at that time, they were considered bulky and ugly, so he called it a heater cabinet, and it looks a lot like a convector that we sell today. So it's, if nothing else, it's a design that's ageless. In 1938, it came out with the first CenTraVac chiller. Now, this may seem to us that's a big deal, but at that time, if you remember that, and I guess even Al and I don't even remember that, right? If you wanted to put a chiller in your basement, you bought a compressor from Carrier or from whomever, Worthington, and then you went somewhere else and you bought the heat exchangers, then you piped them all up and tried to make them fit. So the concept of a packaged chiller was pretty revolutionary, very revolutionary at the time. So you can imagine that, when people saw that, they were buying them. So that was the first hermetic. It used Freon. I thought it was kind of cute in the catalog. They called it Freon. I had to look up which Freon it was. Haven't heard that word in a long time. And it operated about 1.12 kW per ton. Not too bad for a 75-year-old chiller. It probably cost about $6,200 if you wanted to buy it for a 500-ton machine. And at that time, you could buy gas for a dime. You could buy a new car for $700. Not the Duesenberg that Mark drives, but you can get something. And that was the first year for Superman, and oil was discovered in Saudi Arabia. So a big year in 1938. So let's take a look at our next, excuse me, got ahead of myself. I thought this was kind of interesting. There's actually another set of impellers down here. It was a 4-stage hermetic, direct drive, low speed. Did I say low pressure? Low pressure chiller. I thought it was kind of fun. It looks like a fin tube heat exchanger there, so he was going to really milk that technology to where we go with it. So I've never seen the inside of one of those, but I have seen an impeller from it. It's quite a work of craftsmanship. They were all handmade, hand brazed out of bronze or something. So pretty impressive. So the real CenTraVac probably was 1951, and I want to take a second. I want you to appreciate that design. This is a 2-stage chiller. The motor is actually between the 2 stages, and so you can't see it, but the discharge of this stage wraps around and comes to the intake of this stage, and then in turn pumps it into the condenser. So it was introduced in 1951, and I've actually sold a couple of these. So they actually went all the way up into the late 70s, this style on the very smallest ones and on the very largest chillers.
We still have 2 of those in operation in Asheboro.
Is that right?
Yeah, the serial number are 3 digits now. They're 1950.
Wow, did you convert them to 123? They also ran on Freon 113, 1.08 kW per ton. How much do you think gas was? So the chiller was about $11,000. Gas was 19 cents a gallon. New car was $1,500. Rock and roll was coined. Still use it. 1951. I forget the guy's name. Friedman was a disc jockey in Chicago. He came up with the terminology the first time. UNIVAC was the first computer. I'm told that the UNIVAC had the computing power about half of a hand calculator, and it might have fit in this room, but I'm not 100% sure. And of course, for all the bachelors out there, the pot pie was invented: chicken, beef, and turkey. Or some other folks out there. Been known to have the pot pie myself. Okay, so here's one I got from a friend of mine in Texas on its 50th birthday. It's still running. And now that we have one in Asheboro, I probably should have been more local. I apologize for that. It's still going. It's been running day and night in a museum in Dallas. And here's some smart guy doing his logging, which of course he did every 2 hours or so. I didn't know the operators had to wear coat and ties in those days, but I just wanted you to see what the whole chiller looked like there. There's that first suction line that you couldn't see in the other picture. The next was we call the Sidewinder, and we actually turned the impeller sideways and made it very compact so it could go into smaller space when you go in the door in 1964. 0.8 kW per ton, getting better. About $13,000 for the chiller. And gas was getting up there to 30 cents a gallon, get a new car for $3,500. Not quite the year I bought my first new car, but we're getting close. The Rolling Stones released their first album. They just released another one. So they've lasted longer than a lot of these chillers, although we have quite a few of them left. And the good old computer mouse, what we do without our mouse. Here's a couple that were you can guess where those are with the restraining straps in San Francisco. Keeps them from falling over during an earthquake. They looked into possibly upgrading to digital controls. Somebody suggested maybe they got their money's worth out of them, but we'll see what they do. We also had an air-cooled CenTraVac that came out in 1972. We sold a lot of them in the United States, but primarily went overseas into the desert. And we actually made that up into the 80s, and then it was finally replaced. We moved the production over to France, kept making it for the Far East, the Middle East, and then we came out with our screw compressors, and it kind of phased that out. It was kind of neat. There was a mechanical room built onto it, and you can actually go inside and service it, you know, when it was raining or hot or too cold. Actually, the standard unit had a little unit heater in it, and the ones for the Middle East had a little fan coil in them. So the guys that needed a little afternoon siesta had a good place to go. I'm pretty sure it's used like that more than once. This is the flagship that came out in 1982. This was truly revolutionary. Three-stage, it was 5 to 20% more efficient than anything on the market. 0.65 kW per ton, it was almost unheard of at that time. We hit it right after almost right after the second energy crisis. The world was looking for efficiency, and we just really hit a home run with that. It's basically the same design we're using today on our production chillers. Cost about $42,000. Gas was up to $1 a gallon. That Cadillac was $8,500. Lotus 123 as the first killer app for the PC. Anybody heard of that? Lotus 123. When computers first came out, you know, the sales guys, a little computer store down the street, and we'd all go on the computer, look at these $5,000 IBM PCs with 64K of random access memory. And we're like, God, I really want one of these, you know. And we're like, what do we do with it? So we asked the guy, what do you do with this thing? He said, what do you do word processing? I was like, what's that? I looked at word processing. And you can do spreadsheets. And I'm like, what's a spreadsheet? Now think about this. If you'd never seen an Excel spreadsheet, someone said a spreadsheet, you're like, you had no idea what that was. And at that time, Lotus 123 essentially sold the IBM PC. We sold the first air conditioning system for the original fabrication plant, which was a little machine duplicating 5-inch floppy disk that was all, you know, sat in the corner of the room, a huge room like this, and ultimately they filled it up and they were very successful. I think digital equipment bought them out and they kind of faded out of the woodwork, and today we use Excel for the same reason. Wayne Gretzky had 92 goals. We had a chance to go to the hockey game last night and saw a lot of goals. It was fun. Wayne wasn't there. He moved to Phoenix, of all places, moved his team to Phoenix. What a contrast between, where was he, Edmonton or something? CVHE compressor, also note, here's your motor shaft, and there are 3 stages were directly connected to the shaft, and we can do and there's 3 stages of compressor. So it's like, why do we want 3 stages? Okay, well think about this. I can probably get up on this stage right here without the stairs, okay? And at my age, you know, that's 1 stage. It's a lot easier to get on the stage by going up 2 stairs. And if you're a little higher, I could have 3 stairs. And that's kind of logic behind the staging of compressor. It makes for less work and more efficient operation. That's where the 0.65 or better kW per ton came from. The CVHF came out similar to the CVHE with only 2 stages, and their new refrigerants at that time, 123, worked better with 2 stages, so on the larger sizes. And we took out one of the stages, and we also cut a little cost out of it. 0.55 kW per ton, about $65,000. Gas, car, not a whole lot going on there that I could find that was exciting that year. Although, that was the year I moved to Arizona, so it wasn't totally unexcited, but I didn't feel like it deserved to go on that list, in case somebody else used the slides. And then the duplex, which has become a very, very popular machine, came out in '96, 0.48 kW per ton. Some of the selections will have either 2 or 3 stage compressor on them. Gas, and again, eBay was started, and old Dolly was cloned. I want to take a second and look at that again. Let's look at this duplex. If you're going to put 2 compressors on a chiller, there are 2 ways you can do it, at least 2 ways you can do it. One would be to put the compressors on the same refrigerant circuit. The advantage of that might be that when you're running at half load, you've got a 1,000-ton compressor going to 2,000 tons of tubes, and you could get a fairly efficient chiller out of that. You do give up any redundancy that might come in that. The other would be to put 2 separate circuits, kind of circuited normally, and then third, what we did is not only do we have 2 separate circuits, but they're thermodynamically counterflow stage. So what's the big deal on that? Give me a second now. If you're making 40-degree water, can you make 40-degree water with 45-degree refrigerant? And I'll answer that for you. No. So the refrigerant has to be colder than the water. And conversely, if you're going out of that condenser at 95 degrees, then the refrigerant's going to have to be above 95 degrees for that to work. That's, I learned that at NC State. It's not a Trane thing. Yeah, it's like the first law of thermodynamics. So the horsepower it takes to cool is moving a certain amount of gas from here to here. You're lifting it up, and that's called lift, okay? So what we did was, if you can imagine these 2 chillers kind of put together, and you could look in here, the first stage, or the downstream section here, is seeing 48-degree water to 40, so let's just say for the sake of argument the refrigerant's at 40 degrees, and then the condenser side, it's seeing 91 degrees, okay? So that's essentially a 50-degree lift. By the same token, I can make the same story for the second half of the machine, and we'll see another 50-degree lift. So we're doing that kind of in 2 steps. If we had a single-stage design, like some of our competitors, we're going to have to raise that one shot from 40 up to the 95, which is I can't do it in my head, 57-degree lift. So if the horsepower to do that work is the amount of flow you're making, which is the 2,000 tons, against the lift, then thermodynamically, that's gonna be more efficient. So that's where that efficiency comes from. And on very large plants, we'll even put 2 of these in series, and then you can start, doing the mental math on that, and you end up with even a better situation. And we're starting to see these chiller combinations, pushing, 4.2, 4.1 kW per ton. So you can do a lot with the duplex by itself, and then you can pipe it in very different ways to get some real performance out of it. Pretty innovative. Don't know who invented that. So what are we doing now? We're just introducing the first of a new line of chillers called the CDHS, and we actually had a CDHS 10 or 11 years ago, and basically it was our CDHE with ceramic bearings that were lubricated by refrigerant, and so it was an oil-free design. And when they announced it to me, and I'm a pretty good CenTraVac guy, I'm like, it's a big deal, And the customers at the time, what's the big deal? Well, subsequently, we're seeing more and more oilless designs, and people are realizing, that oil can get in the way of an efficient chiller over time. It can, that oil can get overcharged, and you start having oil hanging up in the machine. It takes away the heat transfer surface, it can coat the tubes. So there's a lot of long-term performance issues with oilless. So we figured it was time to do it. We also had to do one other thing to make it work. Remember I showed you that 1951 chiller design? Look at that compressor here, okay? We're taking the suction out of here into this first stage of the compressor. It discharges here, and it goes into this compressor, and then down to the condenser over here. So it's the goal, this is a blank sheet of paper, brand new chiller. We introduced it at ASHRAE. We can select it today. It'll start shipping fourth quarter, a couple of months. It needed to be the highest efficiency, quietest, most reliable, and field serviceable. And there's a few new things that we included. One was what we call a specific speed compressor, and I'll tell you what that means in a second. Permanent magnet motors, basically a synchronous motor lives at certain RPMs, 1600, 32, 3600, 1800 RPM, 1200, you're stuck with certain RPMs. A permanent magnet motor doesn't care what the RPM is. Secondly, there's no slip, so it's a little bit more efficient, and it maintains its efficiency as it unloads, unlike a synchronous motor. So, permanent magnet motor, and then we have a Trane design AFD. We call it 3 for our third generation. That will come with that, whether you like it or not. You will not be able to buy that with the start. So let's take a look at the compressor. The challenge with the oilless design on the 3-stage, if you remember how those impellers were lined up, they're kind of like soldiers, okay? So as they spun and the air and the refrigerant came in, it caused thrust, okay? And so if you have a thrust bearing, you need lubrication. It's really hard to design an oilless thrust bearing, and that's where we were having some challenges on that design. There's ways of getting around it, but it didn't work. It didn't do as well as we would like it. So by arranging the impellers this way, you'll notice here's the inlet here, and here's the inlet there. We're offsetting that thrust, so there's no thrust on that whatsoever. It's just a pure circular motion. So now we can put the ceramic oilless bearings in there and not have to worry about the thrust on it. The second thing is that these impellers are a little bit different than what we've seen before. They're mixed flow. The way it was described to me, if you could think of a jet engine, the gas goes through a jet engine, that's axial flow, goes straight through, or a propeller fan even. And if you think about a pump or a plug fin, the air comes in and then goes off radially, that would be centrifugal flow. So a mixed flow is a combination of those two. And so it has some of the benefits of both, the actual being high volume and the radial being high lift. So this impeller is a little bit wider, and then inside of it, instead of the blades kind of going straight, they have some configuration to them. So this compressor is refrigerant agnostic. We can design it for whatever the next refrigerant is going to be. So I'm not a manufacturing guy, but it's unlikely to be, and they don't tell me everything. Then 2013, we got to spend tens of millions of dollars on a new compressor design for refrigerant we're only going to be able to sell for 7 more years. Would not be very prudent. So as you can imagine, this is I think what we're going to see, and that's going to only expand more as time goes on. I got ahead of myself, multi-stage mixed flow impeller. We're using 123 refrigerant with the ceramic bearings, oil-free design, and I talked about the permanent magnet motor, the FD, etc. So pretty excited about that. Got a lot of buzz in Dallas when we introduced it. First really new thing we've done in a while. Designed to go through a door for retrofit applications. It'll come apart with specific lifting points so that you can rig it into an existing building or through a window if you have to. Here's an example of some of the performance, and this is better than anything you can buy today in this size range. Right now it's 180 to 390 tons, so we start on the smaller sizes. But as you can see, it's a 300-ton chiller at full load of 0.5 and a high PLV at 0.318, so pretty darn good. Okay, CBHL is a modification of an existing chiller. I won't spend a whole lot of time on it, but basically we're finding people looking for chillers making 55, 60, 65, even 70 degree water. We call that low lift. Talk about that lift concept, okay? So this is not unlike what we make on the CVHF, but by some modifications. Primarily, I'll show you inside the compressor, we're improving the performance versus our chiller that doing the CVHF doing the same thing of 10 to 15%. We haven't quite gotten the AHRI approval published yet. We have it, we just haven't published it yet. So I can't show you an example like I did on the other one, but starting whenever we get when's the next replication coming for Trane, another couple of weeks, then it'll be in the selection program. We'll be able to actually select one. Why would you use it? Data centers is probably the biggest thing. We do really well with data centers. And then as they're taking warmer and warmer water, save energy, you know, it's getting made it worthwhile taking a good hard look at that and seeing if there's anything we could do. Chill beam's another one where you might want to see some warmer water to keep the dew point up on the chill beam. Basically what we did is took the first stage compeller out. Pretty clever, huh? Left one stage in there, needed some aerodynamics on the inlet there to make it work. Requires an AFD to make it work. We did some stuff with the refrigerant management system, so we ended up with a more efficient chiller. Actually costs a little bit less. So I don't know about you, but if you can get that, that's approaching the holy grail there. Get more efficient for less money. Doesn't happen very often. No trade-offs there. So that's kind of our line. As you can see, there's the overlap there. This is a premium product right now. It's a higher efficiency. It's going to be a little more expensive. That's what premium means. You know that, right? So you'll still be able to buy both of them depending on the application, depending on the budget and the requirements. So over the years, we're still delivering reliability, efficiency, and whatever the last one is, lowest emissions. Many years of low pressure, low speed, direct drive centrifugals, and we're real proud of them. So where do we go from here? We talked about the lift, you know, the heat transfer today, the refrigerant, the difference between the refrigerant temperature and the water temperature is less than 1 degree. So if you threw more copper in there, it's still gonna be below 40 degrees. Maybe you can get the refrigerant to 39.999 instead of 39, okay? But there's, you know, there's not a whole lot you can do to really improve the heat transfer on that. Compressors have been tweaked over the years, so they're pretty close to the theoretical best. So what are we going to do? You know, what are we going to do in the future? This was the history. This kind of repeats what I showed you, you know, slide by slide. Today we're down around 0.5. Well, we're going to look at the chiller plant. That's what we're going to have to do. We're going to have to look at the rest of that chiller plant. We're going to have to figure out how to operate these chillers in unison. Not too many single chiller plants today. This is just I just grabbed some numbers for a full load chiller plant, 20 feet ahead on the condenser, 60 feet on the evaporator. And at full load, we're starting at about 1.25. I want to just have a basis of discussion, kind of, for order of magnitude for you. This is something excuse me for a second. This is something I got off the internet. I don't, from a Hartman company. They make high performance software and hardware for chiller plants. And I don't have any data to back this up in terms of whether this is accurate or not, but I feel like it's pretty good. And this is an annualized chiller plant efficiency. So that would be all your ton hours for the year divided by, all your kilowatts for a year divided by all your ton hours for a year. So you get some sort of an average kW per ton. So it's not full load, it's a little bit better than full load. Think about the weather gets colder, so your chillers could run a little more efficiently. There'll be times that maybe you're running 2 instead of 1, that helps you. So there's a lot of plants that are out here, okay? So somewhere in this range here, 0.5 might be pretty close to as good as it gets. So if we can get down into that area, I think we got something. You know, compare that to the full load of 1.25, even with a very high performance chiller. So let's see how we can do that, and let's see what that looks like. And I just want to tout, in October, we're going to have an engineer's newsletter, and an engineer's newsletter live, where people way smarter than I will go through this step by step including the pumping issues for variable speed pumping on a condenser and the cooling tower, and also on the chilled water pump. I want to spend a little time on the compressor because we're kind of talking centrifugal chillers, and I'm just going to give you some sort of summary on the effect on the cooling tower pump and on the tower fans. But definitely you're going to want to see that. I think you're going to enjoy it. One thing we're doing, and we're studying that, we've got a field trial going so that so the math we're doing to optimize these chiller plants, we can test it out and make sure it does what we promised. But there's a lot of factors that go in there, anywhere from ambient, the load, of course. We got limitations on a lot of the equipment, whether it's a pump or a cooling tower, for varying flow and a cooling tower. We got surge, and we've got other things that we'll talk about in a second. So, you know, there are some things that we have to kind of dodge while we're trying to optimize all that. So it gets really kind of complicated. When people think variable speed, they immediately remember, you know, that square term where power is a cube of the change in volume. So that's kind of theoretical best. And in pumping, that's, you know, we start approaching that, but when we talk about centrifugal compressors, we don't. And again, we'll talk about that. But just want to establish that sort of as another sort of reference point. So the cooling tower fan, the tower energy use can vary greatly. You have options of running 1 cell, 2 cells on a multiple chiller plant. You've got to sort that all out, okay? The wet bulb has a lot of effect on what we're going to get out of that. We can run all the fans we want, but the wet bulbs at 67 or 68, there's only so much we can do, you know, or 72 even, that we can do on that temperature, no matter how many fans we run. So there's some serious weather restrictions on that. So reduce energy use on the compressor, but then you're running more fans. So these are all things that we need to factor into that discussion. Condenser water pump, the energy probably follows that square relationship pretty well. But, you know, again, with the analysis, when you're running that condenser water pump, are you going to force it through 1 tower, or are you going to put it through 2 towers? Now you're looking at different paths, so your pressure drop changes. Then we also run into minimum flow issues with the chiller. We got to make sure the tower fill stays wet. And then we have to make sure the pump can operate over that whole range. So again, there's some restrictions and some considerations when you start talking about fully optimizing a chiller plant that have to be factored into it. And we're doing a lot of work right now to do that. This guy at Trane, his name Brian Sullivan, he's got like 20 patents. He's sort of like invented part of the CenTraVac. And I think he's like my age, and he wanted to kind of slow down, and he was getting tired of, you know, designing impeller passages. So he's now working in our applications engineering department. He used a lot of tools he had for compressor design that he can apply to the operation. And I love listening to him because he's a pretty smart guy. And so a lot of this work he's doing with us. And then we have some other smart people doing it. So let's take a look at the compressor. That's sort of the theme of today. That's what that impeller looks like if you were to take it out. How do they unload? A constant speed uses an inlet guide vane, much like an old style fan, and it pre-rotates the gas that's going into the impeller, and the impeller changes its curve, so to speak, and it moves less gas. With a variable speed fan impeller, we change the speed of the motor, and then it'll move less gas, much like the fan. The challenge with a compressor is called a restricted or constrained device, and why it doesn't follow that beautiful tube relationship is that I think it's either, I always get Boyle and Bernoulli mixed up, but one of them said that gas wants to flow from a place of higher pressure to lower pressure, so the gas wants to go that way, right? So if you can picture a compressor, this is the low pressure side, that's the high pressure side. Which way does gas want to go? Well, it wants to go that way, according to Bernoulli, right? But according to Trane, we want to go the other way. So we spin this thing fast enough to force that gas to do what it doesn't want to do. So you can see at some point, if you make that too slow, the gas is going to follow Bernoulli's rules instead of Trane rules, right? Called surge. So every single chiller with a VFD on it also has inlet vanes to, you know, to take that other part of the unloading curve beyond where it can do it without violating Bernoulli's rules. So, and so that also will affect our control and how we do the tower and how we add this all up. So let's keep going. All right. You ever been to a Trane seminar without a graph? I couldn't force a site chart in there. I'm really sorry, but I just couldn't do it. Okay, let's take a look at a constant speed compressor with a constant enter condenser water. So this is what that curve looks like as it unloads. You're going to get some little bit of help as it unloads, but that's not too exciting, I don't think. But one thing that people maybe don't realize that is we put 75-degree water, even with a constant speed compressor, that's going to help us a little bit. Okay, and we can do that again for 65 and 55. As you can see, the curves have the same characteristic shape, but they just start at a lower point. So let's take a look at a variable speed compressor. That thing always keeps popping in there and I forget about it, so I'm sorry. Rehearse this a little better. Let's look at a variable speed compressor. Here we are at 85 degrees again. And notice that the shape is similar, but the curve is different. It starts, we start seeing colder and colder water, that dips a lot more. And I'm going to put the other one on top of it. You don't have to mentally draw the constant speed compressor. Let's do that now. This is a little bit hard but let's stop for a second here. The yellow that's constant speed variable. Okay, constant variable, constant variable. So you can see there's a, at 60% load, depending on the condenser water temperature, the amount of help it gives you is a lot more at 55 than it is at, say, 75. So it's not linear. So now we have another quadriplegic, quadratic equation or something to try and simulate that inside of our automation system so we can figure out how that works. But one of the things we can observe at high load and no matter what the lift, they're very similar. That makes sense. At full load, you're going to run your variable speed chiller pretty close to the same as a high speed chiller. But even though you can unload a little bit, it still doesn't help you that much. At high lift, in fact, it can actually hurt you. The constant speed is actually a little bit better at light load and high lift. But where we really see the advantage is that a combination of lower lift and lower load. So that's where the AFD really shines, and we like to factor that in. We're starting to see people maybe, instead of buying, you start getting into some large chiller plants with medium voltage motors on it. You can spend almost as much for the drive as you do for the chiller. So people are starting to think a little bit differently. Maybe they only need to put the drive on one of the chillers, or maybe they've got winter chillers that have the drives on. A lot of different ways and creative ways of looking at that to work the pricing out. So, what do we learn? We want part load and part lift for the benefits of the variable speed. There are limitations based on the condenser and the evaporators we saw, and it's not proportional. So, let's put this all together and see where the potential is. Where can we really make some hay out of this? Brian took a building in Chicago, pretty typical. He's looking at it with 1, 2, or 3 chillers. We want to look at the effect of the number of chillers in the chiller plant. We want to look at the effect of whether or not it had drives on them, etc. So I'm going to give you a second to orient this, but here's a constant speed chiller with a 1-speed tower fan, 3 GPM per ton constant flow condenser water with a fixed 85-degree enter condenser water. That was what it is. There's that 1 kW per ton at full load. That's even better than the one we had. Okay, so with a single chiller, take that back. This is not full load. This is annualized system. Forgive me. So we're off in that right-hand side on that curve we did of we could use some help. Don't forget we want to get somewhere between we're looking for 0.5 to 0.6 would be a reasonable goal for an annualized energy savings on a chiller plant. So that's kind of our starting point. It's kind of interesting that multiple chillers kind of help us on energy. But do you see very many single chiller plants with centrifugals in them? Anybody? I would think they're pretty rare, but some of the older ones might be. I went to a job site in an old Sears store in Boston. Now retail, I mean, they're really weird about their air conditioning. They have more redundancy than a hospital sometimes, you know. And this thing had a single chiller in the basement and been running for like 40 years, you know. I said, why don't you just replace it? You out of your mind, we gotta put 2 of them in there. Okay. So they put 2 of them in. Okay, so what happens if we optimize that? And we're trying to do, and we talked about all these different variables. Let's get the exact right tower fan, the exact right loading on how many chillers run, what flow we want through on the condenser side. Probably gonna get some help there. So we take it now from on a 2 chiller plant from 0.98 down to 0.7, you know, 12 to 15% improvement. That's pretty worthwhile, strictly by optimizing. And that's with constant speed everything. Okay, so let's take a look at variable speed on the condenser fan. Oops. There's our starting point. If we optimize that, okay, we can pick up a little bit more time. Anybody have chiller plants that run at a constant 85-degree entering condenser water? It's amazing how many are out there, you know. Consulting engineers spend all this time and effort to do the best selection with a good part load and IPLA and all this stuff to get the best selection. And the second day, the old school operator, been there for 100 years, comes in and he said, you know what, I don't care what those engineers say. Let's set that condenser to 85 degrees. We won't get any phone calls. You know, we're not worried about that chiller going down. So it happens, but we're seeing less and less of that. People are beginning to see the advantage of doing more with their controls as it relates to condensed water. But they're still out there. Okay, so let's look at a variable speed chiller, variable speed tower fan, okay, constant 85-degree entering, and then look what happens when we optimize it. I mean, that's pretty huge. So we can see why probably, I don't know the exact statistic, but it's in the neighborhood of 55 to 60% of the chillers we make today have drives on them. So even if you don't optimize it perfectly, then you have an opportunity to really save some energy putting a drive on a chiller. And you can see why our next line of chillers, we're not even messing around with starters. And you know, if I were buying an air handling unit today, I would put a starter on it. You can buy a drive for the same price. You know, there's no reason to use the starter anymore. The pricing has gotten so good. So finally, I'm going to kind of skip through this a little bit because we're changing more than one variable, which makes it hard to follow. But here we're getting down to 2 GPM per ton constant flow optimized, and they start to come together. But it's interesting that the 2 GPM can save some energy, but if we go to 3 GPM, okay, it actually gets a tiny bit better, and that can vary depending on the head and the flows and blah blah blah. But not a whole lot of difference. So maybe a little bit academic at that point. Finally, we can go with a high efficiency variable speed, optimized everything, you know, top computer models, and now we're approaching, even with a single chiller, we're back in that 0.5, 0.6. With multiple chillers, we're right around that 0.5. So we can do it. We can do it, and we want to do it. Wait a minute, get ahead of myself. What do we learn? Multiple chillers, okay? Optimization, these are 2 things we really want to look at. That's the future for us, okay? Particularly the optimization. Adding VFDs need to be controlled properly, but they can help, all right? There's a wide range of improvement. You know, we went from 1 to 0.56, that's almost a 50% improvement on a single chiller plant. 30% is still pretty impressive on a multiple chiller plant. You know, many of them are running not only at 1.0, but you know, 1.0 is theoretically running properly. You know, you get some dirty tubes, you get some other issues where they're not being controlled properly, or they're fighting themselves. They can get worse than that. So once again, we're going to go over this in more depth with our Engineers Newsletter Live. We're also going to be introducing, sir.
Can I ask a question?
Yeah.
You used kind of a generic term called optimization. What does
Yeah.
that mean?
Question was, what does optimization mean? And we use it as a generic term. I talked about, you know, how the cooling tower fan has to be, you know, you can change the speed of the cooling tower fan, but we have to, or let's look at condenser flow because we don't do that so much. We can change the speed of the condenser flow, but we got to worry about make sure the tower can handle the flow. Do we want to run the condenser fan hard and the compressor light, or do we want to run the compressor hard and the fan lighter? You know, let's say, I jump around a little bit, forgive me, but let's say you have your tower fan, okay? You have the opportunity on this day, if you can run the tower fan hard, I can get 65-degree water out of it. If I run it, you know, if I slow that fan down, I can get 75-degree water out of it. Am I better off running 75-degree and make the chiller work a little harder, or should I make 65-degree, make the chiller work a little less? If I've got a 2-chiller plant, I have a 50% load. Should I run 2 chillers at 50%? Should I run 1 chiller at full blast? These are the types of things that we're going to optimize in order to accomplish that.
Okay, I understand the engineering concept.
Okay.
What does the optimization? Do you have operators sitting there?
No,
Or do you have a control package?
that's what I was gonna, there's no such thing as a free lunch, so I was gonna talk about that for a second, without making it too commercial. We call it Earthwise Elite Chiller Plant. Right now it's a working discussion, and we will have a package that you can buy, and it's not gonna be a customized deal where, you know, we want $100 up front and $20 a year to keep it going, all right? We're a product company. We want to turn this system into a product. So what do you got to do to do that? Well, you need to try and get 70 to 80% of the applications. You need to make it editable so that you can plug in different size chillers, whatever, without having to rewrite all the code. Has to be tested out. We need we want to create some dashboards so you can see what's going on in real time. You know, what's this plant doing, so that people can actually try and experiment and see if they can beat the optimization. We also invented something called mode charts. I'll show you what that looks like, and then we have the literature and applications guides, so that it's transparent to you, give you an idea of what we're doing and why we're doing it. And I'm on that team. We're working hard to get it done, you know, somewhere in September, October timeframe. And we want to be able to introduce that right around the same time as the engineers newsletter. They're designed to kind of coincide together. We'll give you a lot more detail on what that looks like. But one of the tools we've developed as part of our automation system, part of our dashboard graphics package, is what we call a mode chart. We have an Earthwise Elite system that optimizes variable air, good old-fashioned variable air. 25 to 30% more efficient than traditional variable air, more efficient than VRF. And one of the tools that's part of that is a mode chart. This green bar will move depending on what mode that air handling unit's in. So that somebody who's not that familiar with the job, or we hadn't had technicians tell us, you know, they get called on a job, and got 5 people breathing down their neck, what's wrong, tell me, fix it, too hot. Maybe they've never been to the job site. They don't know what the air handler is supposed to be doing in terms of what mode it's in. You know, maybe it's in morning warm-up, and it should be in occupied cooling. And so this will tell them exactly what mode it's in. And not only that, it'll say, okay, what's the fan supposed to be doing when it's, I can't see it. But, so here's unoccupied humidifying. You know, what's the fan supposed to be doing? What's the outside air damper? What are the coils doing? What are the VAV boxes doing? So they tell them at a glance exactly what's going on. And then it's designed to be printable so someone could have reference to that. That's an example of some of what we're trying to bring to the party to help enhance the offering that we have for the world here. I think we're getting a patent on that. It came when we did our first, call it ice enhanced air-cooled chiller plants. And we created a mode chart. You're kind of used to that, you know, you're an ice build, I need this valve closed, I need this pump on, I need, you know, the chiller running at that temperature. We're kind of used to seeing that. And the computer people didn't know that we don't use mode charts on air handling units. We only use them on ice storage systems. So they went ahead and made that and said, yeah, pretty good idea. So we decided to keep it in there. Pretty cool. So this is what we'll have in that package: 1, 2, or 3 chillers, CenTraVacs, constant or variable speed. So you could have a hybrid where they could have a combination of constant and variable speed. Variable speed cooling tower fans, constant or variable on the condenser ones, and they'll all be designed for variable primary on the evaporator. So that's the package that we'll have available to you. Fourth one. All right, how are we doing that time? Getting a little, I'm going to spend as much or a little bit as you want on the refrigerants. If you need to leave, I won't, don't be embarrassed to take off, but I think a lot of people ask about refrigerants, so I'm gonna go ahead and do that, that's okay. Okay. All right, this is a history of refrigerant. I'm not gonna go through each one and tell you how much it costs, because I honestly don't know, but all I know is in the 40s, sorry for that being so light, they weren't worried about the atmosphere. They were worried about this stuff killing you. So, I don't know what ethyl chloride or methyl chloride is, but I don't want to drink it, eat it, or smell it. Okay, so that was one of the beauty of the Freons, was it totally got rid of all the explosions and deaths that came from refrigerants in those days. So at that time, we've gone through 3 or 4 generation changes of refrigerants. So at that time, it was purely the material they needed to do something about the material on that. Right in the probably the mid-80s or so, we started noticing the ozone hole opening up. So the next round, talked about ozone depletion potential. And these are all the refrigerants that were available at the time. Blue would be the ozone depletion potential. Red is the global warming potential. We were talking somewhat about climate change at that time, but ozone was a big deal. And so all the laws and everything came out. Let's get rid of all the ozone. So you can see, well, CFC 11 is the worst because that's our baseline, but all these old CFCs went away in 1995. When I say they went away, can you buy R11 today? Can you find some? They went away in that they cannot be manufactured. You can't buy virgin refrigerant. But it doesn't mean you can't use it. Okay, and it's an important distinction. Some people forget that, So 20 years later, it's going to be the end of the world, and some of you were around during that time. People were hoarding the R11. They were going to put their kids through college. It was going to be their retirement. It was a stash of R11 they had. When it all, disappeared off the face of the earth, 10 years, and they could sell it for $50 a pound or something like that. I'm willing to bet you there's a lot of R11 sitting around warehouses somewhere that aren't getting used. Okay, so there's that tail lasts for a long time. We learned a lot in the industry about the timing of refrigerant phase outs. We'll talk about that in a second. Over here, we're looking at global warming potential. So first thing was get rid of all the ozone depletion. So the second thing, now we're starting to see the global warming potential. And you can see, where's 134A? 134A, I want to say it's in the 25 to 3,000 range. I don't even know what the units are on that. I'm not a chemist. The world is trying to get the global warming potential at 150 or lower. And that would be 150 times as bad as CO2, CO2 being 1. So that's why we don't think 134A is going to be around forever. As a matter of fact, nobody thinks it's going to be around, even our competitors. But if we look at, get rid of all the fluff there, we look at 123, the global warming, I mean, it's pretty decent refrigerant. There's 134A, you can see that just that little bit there is causing all this aggravation on the refrigerant. Fortunately, our friends at Honeywell and DuPont said, hey, I see an opportunity here. Let's invent a new Freon. Okay? The refrigerants that we use today will no longer be manufactured probably in the next 5 to 10 years. Anybody believe that? Do you believe that? That's a fact. We know that for a fact, number one. Number two, they're not going to give us 40 years to phase it out. We could have done CFCs and HFCs in 10 years. So chances are, when the laws have changed to start phasing out the high global warming potential refrigerants, the manufacture of the high global warming refrigerants, it's probably going to be done over a 5 to 10 year period. And I forget what 3 is. So some people feel it might be in the 2020 to 2025 time frame. Who knows? I'm not smart enough to know that. HFOs, hydrofluoroolefins. I've just told you absolutely everything I know about the chemistry of HFOs. So I will not entertain any questions of that nature. However, they're being developed as we speak. There's a lot of promise on that in terms of either drop-in replacements or legitimate replacements of various refrigerants. I have a chart I'll show you. Europe they don't even need air conditioning, so they get pretty aggressive on what they want. They want everybody to use either butane, imagine 500-ton chiller with 1,500 pounds of butane in it in the United States. I think the lawyers would be like hanging out there. They do use it in refrigerants, but there's probably as much butane in a refrigerator. It's probably as much butane as there is in one of those old cigarette lighters. So not so bad in the refrigerator, but you don't want it in chiller. Ammonia, we can use ammonia today, but you know, if you've ever tried to do a plant, you know it's pretty challenging. And then finally, CO2 has some potential. Anybody know what the condensing pressure of CO2 is? 9,000 psi. Okay, now you got, you know, Joe, residential service tech, you know, shows up. You know, you go ahead and mess around with a 3-ton condensing unit with a 9,000 psi and kill somebody. So a lot of challenges with CO2, but it's, you know, it's environmentally really good. I've seen a CO2 chiller. It's all stainless steel, very, very expensive. And there is some efficiency problems with CO2 also, but somebody's going to make one and somebody's going to be able to sell it. So let's take a look at the timeline. You know, we talked about 1995. That's when we stopped making R11 and R12. And then, you know, we can still get it. Who knows when? We're not going to be able to get any more. Then as time went on, I got ahead of myself. 123 in 2030, we'll stop making 123. So that's about 17 years from now. My math isn't that good. So pretty sure that if you bought a machine today, or even 2 years, 5 years from now, you won't have a problem with the availability of 123. Matter of fact, if you buy a Trane machine today, we guarantee the refrigerant for 5 years automatically. Not the availability, but if you lose some refrigerant, we'll give you under warranty for 5 years. If we service that for that 5 years and continue to service it, we'll guarantee it forever, as long as we're servicing it. So the message I want to get across is it's premature to worry about 123. And if you are worried about it, let's talk. It's a great refrigerant. Got customers now that they want to buy the last 123 chiller that comes off our line, because the HFOs are likely to be a little bit less efficient. They're going to be more costly. There's other challenges on the technology of making the chiller with that in there. So anyway, let me wrap this up a little bit. Going through the options for the refrigerants, we looked at ozone depletion. These guys are gone. Now we talk about global warming. These are fairly high in global warming. 32 is moderate. 152A, is it 152A? Yeah. Here's the new HFOs. The YF is also, if you bought a Cadillac today, they would have 1, 2, 3, 4 YF in it. We're already starting to see that being used. They're stopping using 134A in cars. It's not mandated, but the manufacturers are seeing the writing on the wall. 152A is a good low pressure refrigerant, but it's flammable, and we're not sure how that's going to go. Interestingly, and then we have cost, efficiency, toxicity, etc. The ashtrays create a new category of refrigerants, the 2Ls, and those are for flammable but hard to light, for lack of a better way of expressing it. So what that'll do is they'll create how you do the mechanical room if you use an A2 refrigerant. And some HFOs are going to be in the A2, B2 range. What do you got to do? So you don't have to be as onerous as a highly flammable would be in terms of how that mechanical refrigeration mechanical room is designed. So that's a good thing for our HFOs. This is what we see today with 134A and 123. So chances are they'll be different. I don't know what they're going to look like, but maybe the alarms will be different, something like that. Here's some of the sort of a generic plot of some of the alternatives. You can see we're interested in low pressure. We want to maintain our low pressure, and I'm pretty sure we got a low pressure one because of the design of the new compressor. So we have a lot of choices. and I honestly don't know what we're gonna be using, but probably around 16 or 17, we'll all know exactly what we're gonna use, what it looks like, how good or bad it is, because we as a manufacturer cannot make chillers with 123 after 2020. The manufacturers will not make refrigerant until 123 after 2030. So we have to deal with this in 2020. There's a loophole on the 22. You can buy a condensing unit of R22. It's not charged, and the EPA doesn't want any of that happening again because it didn't really get rid of the 22 that they wanted to phase out the R22. Anyway, the 134A has some efficiency issues. Yeah, and then the square, we would ideally we want them, the green diamond, the yellow square we might be okay with. Forget about the red diamonds, the red triangles. Okay, so we've got there's some hope there. We've got some smart people developing that and creating the various different materials. So pretty optimistic about where we're going to go with that. And we'll have that problem solved when the time comes. So just like we've been talking for the last 25 years, we'll have the right stuff at the right time to give you what you need in the marketplace. That's just an announcement of GM taking out the 134A. So what do you do in the future? Today, efficiency and emissions are just as important as they always were. Lower the efficiency, improve the efficiency, sustain it and document it. That's our Earthwise mantra. You've seen that logo on a number of the booths, or you will see that. We still feel that that's really important. What are the real factors if you look at a chiller, the economic life of a chiller? Well, the most important, the most expensive thing is the cost of electricity over the life of that chiller. 95% of your lifetime cost of that chiller is in the electricity. 5% is in the first cost of the chiller. Quarter of 1% is the original refrigerant charge, and 0.04% is the replacement cost of replacement refrigerant over the life of that chiller. So we just spent 15 minutes talking about refrigerants out of an hour and 10-minute discussion. I'm tired of talking about refrigerants. I love talking about mixed flow impellers and balanced thrust and new AFDs. So let's make sure we keep that in perspective as long as you have what you need when you need it. Let's talk about the technology and let's make it work better. How do you plan? Okay, seek the reliability. We want to make sure that your clients understand where the refrigerants are going. We can help you with that if you need to. We have some experts that will also come out and do seminars if you like. We want to balance the environment, make sure that we look at the meter. That's where we start getting into our chiller plants as opposed to just looking at the compressor. So this is my big close. I want to thank you for your time and for your attention. I don't think anybody fell asleep. That's the first time that's ever happened, and I really, really appreciate it. Anybody have any questions?